This video will explain what ionic radii are and their trends within the periodic table. However, before being able to fully understand what an ionic radius is and what it means, you must first understand essentially how ions work and what an atomic radius is. I will keep this overview of ions brief, as you should already have a good understanding of them through the previous group. Basically, all elements are most stable when their valence orbital is full, so they react with other elements to fill these valence orbitals. This is why ions are generally isoelectronic to their nearest noble gas on the periodic table. There are exceptions to this, however, most notably with the transition metals and certain metalloids. A cation is a positive ion, and an anion is a negative ion. An oxygen ion that is O-2 is an anion, adding 2 electrons, while lithium plus 1 is a cation, taking away an electron. Cat means away, while an means add. One strange trend with transition metals is there isn't one. They will all be cations, and generally they will have ions that are either +2, +3, or both, as they can have more than one ion. Think back to iron 2 and iron 3. However, interestingly enough, their ions can range from between a charge of +1 all the way to +6. Another trend to note is that metals will generally form cations due to lower electronegativity than non-metals. On to a brief review of atomic radius. In simple terms, the atomic radius is the distance from the center of the atom, the nucleus, to its outermost valence orbital. However, it is a bit more complicated than that. As we know, electrons can be found in a certain area of probability. There is not one single defined orbit. One method scientists do to circumvent this is by taking two atoms covalently bonded to each other and cutting the distance in half between the two nuclei. This gives an approximation of the radius of an atom. This measurement is also known as the covalent radius. It is generally measured in picometers, 1/1,000,000th the size of a meter, or angstroms, which are each about 100 picometers. As you go down a period on the periodic table, the atomic radius increases. This is because as you go down a group, you are also adding a new energy level. This new energy level is further away from the nucleus, so there is a greater radius. Additionally, as you move left to right amongst the periods on the periodic table, or in other words, as the group number increases amongst a certain energy level, there is actually a decrease in atomic radius. One might think that since you are adding electrons, there's more stuff, and therefore it has a greater radius. However, one key factor prevents this from being the case. This factor is electron shielding. Take lithium, for example. It has one valence electron and 2 electrons at a lower energy level. The positive nucleus will naturally attract the negative valence electrons and pull them in. However, there are also the other 2 electrons at the lower energy level. These electrons repel the valence electron, essentially shielding it from the nucleus. Their repulsion is relatively strong as they are working together. This is also not to mention the increase in the pull of the nucleus due to the more protons. However, there's a proportional increase in electrons as the protons increase. With that in mind, examine oxygen. Oxygen has 6 valence electrons, and still only 2 electrons at a lower energy level to repel it. As one may imagine, the repulsion force of the inner electrons will be spread more thin than something like lithium. These valence electrons will be pulled more towards the nucleus than in lithium. The main thing to take away from this is that as you move down the periodic table, atomic radius increases and the atom gets bigger. As you move right along the periodic table, atomic radius decreases and the atom gets smaller. The biggest natural element is francium, and the smallest natural element is helium. Now that we have a good understanding of what atomic radius is and what an ion is, we can combine the two to learn about ionic radii. Say you take oxygen. As we know, an oxygen ion is an anion, meaning that we add electrons to fill its valence orbital, 2 in this case. This gives it a net charge of -2. This also gives oxygen a full valence orbital, and makes it isoelectronic to the noble gas neon. Because we added electrons without adding protons, there's less of a pull towards the center, as there is with electrically neutral oxygen. Therefore, the atomic radius of oxygen, an anion, is smaller than its ionic radius. In fact, oxygen's ionic radius is about 126 picometers, while its atomic radius is only about 60 picometers. Now let's take another anion, fluorine, which is to the direct right of oxygen on the periodic table. Fluorine therefore only needs 1 electron to fill its valence orbital, so its ion is F-. Fluorine has an ionic radius of 119 picometers against an atomic radius of about 71 picometers. Once again, the anion's radius is larger than the neutral atoms. However, it is smaller than oxygen. This is because fluorine has more protons than oxygen, so electrons are more attracted to the nucleus. Therefore, for all nonmetals and anionic metalloids in group 15 through 17. As we move right along the periodic table, the ionic radius will decrease, and if we move down a period, the ionic radius will increase, much like with atomic radii. Now let's take sodium. Sodium loses one electron to form its ion, isoelectronic to the noble gas neon. Therefore, the sodium ion is Na+, which is a cation. The atomic radius of neutral sodium is about 190 picometers, while its ionic radius is about 119 picometers. This makes sense because an energy level is being removed from the element, so it has the same effect that moving up a period does on atomic radius. This is seen throughout cations. The cation is smaller than the neutral atom. Now let's take magnesium. Magnesium loses 2 electrons to form its ion, which is also isoelectronic to neon. Therefore, the magnesium ion is magnesium plus 2, which is also a cation. The atomic radius of neutral magnesium is about 145 picometers, while its ionic radius is about 86 picometers. Once again, the cationic radius was significantly smaller than the neutral atom. However, magnesium also has a smaller ionic radius than sodium. This establishes another major trend, that as we move left to right among the periodic table, the cationic radius will decrease. This is because each time we move right, we need to get rid of one more electron to become isoelectronic to the noble gas. Less electrons results in more protons than electrons, which results in more pull towards the nucleus, which ends up with a smaller radius. Additionally, as we move down a period, the atomic radius increases because it gains a whole orbital. Because metals generally form cations, this is the major trend of ionic radii amongst the metals in the periodic table. I have not included many metalloids and transition metals because they generally do not form simple ions, rather many ions for just one element. Delving into that is way beyond the scope of this video. This is just an overview of major trends of ionic radii encompassing the periodic table.